Welcome back to Mechanical Systems Design. In this video, we'll talk about catalog parts. And this is a vast subject, the topic of whole textbooks. So we won't get into a lot of detail, but instead we'll talk about a high-level strategy for selecting catalog parts based on identifying key properties and analyses, then using back-of-the-envelope analysis to set the best values for those properties. As always, it will really have helped to read the topic reading first, and we'll spend most of the time doing exercises. So you want pencil and paper, and if you can connect up with somebody else to work on these together, it makes it a lot more fun and rewarding. All right, so in our topic reading, we gave key properties and a few analyses and some selection guides for fasteners, bearings, shafts, springs, and batteries. And we lightly touched on gears, chains, timing belts, cables, and motors. And of course, we've gone into much more depth in gears and motors in a separate reading and video. And the way we imagine you would use this document is not to memorize it all. And it's not to memorize all of Shigley would not be a helpful exercise. Instead, we want you to sort of have an awareness that these resources are out there, that these guides and analyses are out there. And then when you are designing a machine and you need to pick one of these catalog parts, you go consult the topic reading or text, figure out what are the key properties you're trying to pick, then use back of the envelope analysis, often a free body diagram to understand the loading, and then inverse analysis to set, say, a key geometric parameter for the part. And then do that for all the pieces of your system, and then see if there's any inconsistency, like a shaft that doesn't fit in a bearing, and iterate through the process. And for some reason, I noticed that a lot of beginning designers tend to think maybe I could just use my gut to pick catalog parts. And well, it is the case that there are more nerve endings in your gut than there are in your brain. Now, some of you might be saying that's not true. You looked it up, but you probably looked it up in a book. And I looked it up in my gut. And my gut tells me that this is how our nervous system works. So to quote the great Stephen Colbert in one of the great roasts of all times. So no, following our gut on this generally won't result in very good performance. We may end up with bearings that crunch or shafts that are 10 times bigger than they need to be. So it really is worthwhile to do the analysis, and it usually doesn't take very long. So today we're going to do 3 exercises, and this first one is the selection of a machine screw. Now this might sound kind of boring, picking a machine screw, but it actually it's a process that we very frequently encounter when we're designing some kind of machine, and it's a frequent source of failure in mechanical systems, having an undersized screw, and of poor performance due to having a too large screw that's heavy or bulky or expensive. So getting this right is worthwhile, and it can be kind of an interesting intellectual exercise as well. So here's this scenario for our exercise. We've got this bracket that we've designed, and it has, we've decided we want to put screws in these 4 locations here. We've got the side view and the front view from this bracket. There's some sort of hinge here, and there's some arm connected to that hinge, and there will be a downwards force of value F applied to that arm. And then this bracket is going to be mounted through those screws to this wall. All right. And we've got some values for, the force, 100 pounds force. We're looking for a factor of safety of 2. The coefficient of friction between the bracket and the wall is about 0.25. And we've got some dimensions here. The distance from the wall to this hinge is about 2 inches. The thickness of this internal surface on the bracket is about 1/4 inch. And the distance from between the holes is 2 inches. The distance from each hole to the to this hinge point in the vertical direction is about 1 inch. So we want to pick screws that we're going to put in these 4 holes to connect the bracket to the wall. And the first thing I want you to think about before we do any analysis or math is, what is your strategy going to be for selecting these screws? And part of that is think about the very end. What is it that you want to know after you're done with your selection process? What are the key properties that you are going to want to pick for the screw? And then the next thing to think about is, how are you going to get from the information you have to those properties? What are the steps that you're going to go through? All right, so take a moment now, think that through, and if you have a partner, talk it through with them, and then come back. And this should take a few minutes, maybe 5 minutes. So you should hit pause now. All right, great. So sometimes it can actually be a little tricky to think at a high level about how we're going to solve these problems. And it's always very good to do that before we get too bogged down in analysis, which we might end up doing a lot of math that we don't need for the problem. So in this case, hopefully we see that the property that we most care about in these screws is its strength. So, and that is going to be set by the material of the screw and its size, especially the diameter of the screw, that gauge or diameter. And the way that we would figure out what strength we need would be to do a free body diagram and identify what will the load be on this screw. So that's going to be part of our process for sure. And then the other things that we need to know about our screw are its length and the pitch, the thread pitch. And those are things that we can, choices that we maybe make based on some more practical considerations. So at this point, I'd like you to work through the whole process, do the analysis, and try to figure out what material, what size, what length, and then go to mcmaster.com and try to find a part number of an actual screw that you could buy right now if you were designing this system. And this should take a little while to work through all the analysis and get to a part number. So maybe 15 minutes or so, but it's a very helpful exercise. So start working on that now, and you can hit pause and come back when you've finished. All right. These turn out to be a little trickier than they seem, don't they? Very frequently. So hopefully the first thing that you did was to try to do a free body diagram analysis of the system. And what we see right away is that this is another case of a statically indeterminate system. So we have these two screws and some contact forces with the wall, and there are actually infinite different ways that the forces could be distributed while still achieving static equilibrium. And so the way that I've characterized this in this free body diagram is to say, okay, we've got one normal force from the screw and a normal force from this screw at the bottom. I'm saying the two at the top have the same force, the two at the bottom have the same force. That's one simplifying assumption here. And then we've got a force from the wall onto our part that we're characterizing with this 1 point normal force at the top and a point force normal at the bottom, and 1 and then 2, and then a friction force that is along the surface in the vertical direction. And why am I characterizing the forces this way? So let's start with the screws. I'm saying that the screws provide just a normal force with no shear component. Why am I doing that? Because I would like to use these screws as they're intended, which is to be tightened so that they apply this axial force on the screw, rather than using them as shear pins. They're not designed for that, and it usually results in bending in the screw. The screws have complex geometry with these threads, lots of stress concentrations, and they tend to be weak points if you put a screw in bending. So we want to avoid that. Now it's true that maybe if we load this thing up, there could be some friction under the head of the cap of the screw, but the screw inside the hole will be a little bit long, so that deformation will have lots of room to occur, and it probably won't generate a very big shear force due to friction at the cap head. Now on the other surface with the wall, on the other hand, we would expect as soon as you apply some downward force, you don't need any deformation to happen to get this vertical component of friction to arise. And so we're going to say all the vertical force is going to happen from friction at the wall. The other piece of this that we have to think about is how is that normal force distributed? And in the real system, what's going to happen is we'll have some pressure distribution along this whole surface, and it could be some weird distribution of pressure. But we know for static purposes, we could characterize that as a center of pressure and the location of the center of pressure. So one way to draw this is to say there is a normal force, just one, and then it has some distance, say from this corner. And those would be our two parameters that set the location and magnitude of the effective force from the wall onto the bracket. But I found that just like a little bit more annoying to work through the math. So an equivalent way of doing it is saying, I'm going to model that distribution as 2 point forces. And that achieves the same effect by saying if N1 is 0, then all of the normal force is down here, so the center pressure is down there. Or if N2 is 0, all the normal force will be up there, and then the center pressure will be up here. And if these are equal, then the center pressure would be in the middle, and so on. So it achieves the same effect, but it makes the algebra slightly simpler to work through. Okay, so this is the general free body diagram that we've got. And what we're going to see is if we look through our statics equations, we're going to have 3 equations to work with. And then we also have one more equation, which is we know that the friction force is going to be mu times the normal force if we assume a Coulomb friction, or we model this as Coulomb friction. So that gives us a total of 4 equations. But we have 5 unknowns, right? We have F1, F2, N1, N2, and friction force. So just like we said at the beginning, this is statically indeterminate. There are infinite different ways we could achieve equilibrium with these forces. So what do? Well, when we have a statically indeterminate system, the first thing to try is to make a guess as to something that would simplify this situation. And so there are a bunch of different guesses that we can make, and I'm going to work through 3 of them here. And this is the first one. The first one would be to say, well, I would like all the screws to be the same size, so I would like them all to have the same strength, so I would like the forces to be the same on all of them. And if that's true, I would get that the F1 should be equal to F2. So let's make that guess and then see how the loading works out. So we've got the moment balance here, but actually in this case, it turns out you don't really need the moment balance to resolve the system, but I put it down there just for completeness. If we just look at the sum of the forces in the x direction, we know that has to be 0. We have N1 and N2 coming in, and we have F1 and F2 going the opposite direction. But we said F1 and F2 are the same, so it's really just 2 times F1. And so if we rearrange terms a little bit to isolate N1 so we can make it disappear later, we'll get that the normal force at the top should be 2 times F1 minus N2. Then we can do the sum of the forces in the y direction, and there it's pretty simple. We've got the friction force minus that applied load force F. And we know from our Coulomb friction model that the friction force should be mu times the normal force, and the normal force in this case will be the sum of the 2 contributions, N1 and N2. And you could think about it as saying, oh, there's a friction force here and a friction force there, and consider them separately, but you'll get the same exact answer. So if we take that friction force, substitute in here, and then rearrange things a little bit so that we get N1 isolated, we can then substitute in the value of N1 that we solved with our x direction balance. And then we're going to get that 1 over mu times the force is 2 F1 minus N2 plus N2. Okay, those 2 things are going to cancel. And then if we divide both sides by 2, we'll get that the force on the top 2 screws should be equal to 1 over 2 times the coefficient of friction times the applied force, which is the same as the force on the bottom 2 screws because we use this simplifying assumption. And the coefficient of friction was 0.25, so this is 1 over 1/2, that's 2. the force was 100 pounds force. So 200 pounds force is the value of F1. And if we sort of look at this in symbolic form, we'll see that, okay, we've said these two are equal and we end up with 2F, 2F. And then what happens to the distribution down here, if we work through this all and solve for the actual values of everything, we'll get the friction force up has to be F. That we knew already because we've got, it has to be equal opposite to this applied force F. And then the sum of the normal forces has to be 4F. And really we can know that right away by our friction model. We've got a coefficient of friction of 0.25. So to get the vertical component force to be 100 pounds, we would need 400 pounds of normal force. We need four times as much normal force as the vertical component due to friction. So that all works out as we expected. And then this pressure distribution that's implied here is we've got 3F in the bottom, 1F on the top. So the center pressure will be closer to the bottom than the top if we have equal force on both sets of screws. Okay, so that actually worked out pretty well, and we could use this now to select some screws. But maybe you made some different assumptions in your FBD. Let me work through a couple of other options and see what happens. So let's say that you guessed that maybe the force on the bottom screws could be 0 by having only screws at the top. And this will work out. So in that case, we can start with the force balance in the y direction. And we've got, again, F is equal to FF. And the friction force should be mu times the sum of the normal forces. So we get the same this equation which we had last time, 1 over mu F equals N1 plus N2. So N1 equals 1 over mu times F minus N2. If we do the sum of the forces in the x direction, we have that now we've got this 2 components of normal force going one way and just 1 screw force going the opposite way. That's F1. So it's going to be basically twice the force that we had in the last slide. And if we take our solution for N1, substitute in here, again, the N2s will cancel, and we'll get that F1 is 1 over mu times F. And since mu is 0.25, that's going to be 4F in this case. And so 400 pounds. So only screws at the top and double the force. And here's the moment balance just for completeness that we can use to solve for all the forces in our system. And so if we put those back into our diagram like this, we get F down, 4F on the top, nothing at the bottom because we chose to have no screws at the bottom as a way of simplifying things. And then now we've got our pressure distribution has shifted so that we have 3F at the top, 1F at the bottom. So the center pressure would actually be closer to the top in this case. All right. So perfectly valid solution, and we'll be able to use this to pick out screws. Here's one other choice. Let's say that we decided we wanted to make the normal force at the top 0. That's our simplifying assumption guess. Well, so when we do our first moment balance around A, we're going to have, okay, this force has a lever arm of 2 inches. We decided before, or we saw in our setup diagram. These two forces also have a moment arm of 2 inches. But the force that we're going to care about is the net force. So F1 minus N1 times that lever arm. That'll give us our other moment. All the other forces go through point A. N2, F2, and the friction force. They all go through point A, and so they fall out of our moment balance. They don't appear. So the sum of these moments about A is 0. It's 2F minus 2 times the quantity F1 minus N1. But we made this simplifying assumption that maybe N1 is 0. So if we follow through, we're going to see that this would result in the force on the first screw equaling the applied force because they have equal moment arms. All right, now we can do the sum of the forces in the y direction. And once again, the friction force is equal and opposite to the applied force. And that's mu now just times N2 because we've said N1 is gone. And so we now know N2 is 1 over mu times F. And then finally, we do the sum of the forces in the x direction. We have that, now we just have this 1 normal force, N2, and we have minus these 2 screw forces. And if we substitute in, we'll get that 1 over mu times applied force minus the applied force equals F2. So we can solve now for the force on the bottom set of screws. And it will be 1 over mu minus 1. 1 over mu would be 4, because mu is 1/4. Minus 1 is 3, so 3F. And if we put that back into our diagram to see the resulting magnitudes we'd have, now there's no normal force at the top, so the center pressure is exactly at the bottom screw, and the magnitude is 4F still. We always need that total to be 4F. And now the screws have two different forces. The top screw has a force of F, 100 pounds, and the bottom screw has a tension force of 3F, 300 pounds. And this is probably our least useful of the three scenarios that we talked about, because here we have screws in all the holes, and the screws in the top are different from the screws in the bottom. So we're going to need to buy different sized screws and keep them straight. And that might not be, that might be a little annoying. So one of the first two solutions probably makes the most sense. All right, so let's say we go back to our first choice and say, we're going to guess that these screws both have the same force. And it's going to be 200 pounds force is F1, and there are two screws. Remember, there were two holes side by side. So each one would have 100 pounds force. But we want a factor of safety of about 2. So we're looking for a breaking strength of around 200 pounds force. All right. Now we've got the loading required on our screws. We can start to make decisions about the things that affect its strength. And the first choice is what material. So what I'd like you to do is think about, take a moment, pause the video, and think about what material do you think we're going to want for this screw. All right, did you come up with a guess? In this case, you know, very frequently it's nice to have a really strong material, and especially a material with a good strength to density ratio. That's a commonly useful material factor for these kinds of mechanical elements. And hardened steel is really good for this. And that will result in a small component, so it will add less space to our system. And if these are chosen optimally, it'll result in a component with low mass. And hardened steel screws are ubiquitous because of these reasons, and that also results in lower cost. So hardened steel is probably a good choice here. And then we need to think about what size screw. And so what aspect of the size of the screw is going to most affect its strength, and how will we select that value? So I'd like you to think about that independently, and maybe even go and try to find the answer for this. And that could take a couple minutes, and then come back. So hit pause now. All right, did you find one? So the aspect of the screw that will most affect its strength is its diameter, or its gauge. And one way to look up a screw size appropriate to a certain axial load is in a table. And we provided one as an example in the topic reading. And if you go to that table, you'll find that a 440 hardened steel screw can take about 200 pounds of load before breaking. So that would be a good choice. And the 4 here is the gauge that's going to set the outer diameter. And the 40 is the thread pitch. That's 40 threads per inch of screw length. And then, so our last thing to choose is what length of screw do we want? So take a moment, think about what is going to be important about how's that length choice going to interact with important things in our system, and then try to work out exactly what length we're going to want in this case. And hit pause now. It should take a couple minutes. All right, did you come up with a number? So there are a couple of factors that we're going to want to think about in this case. One is the thread pull-out strength. So we don't want to strip those threads. And a common heuristic would be we want 3 full threads into the wall to get the adequate thread strength. And let's say we add a factor of safety on top of that and say we're going to go for 6 full threads. And that would mean, so each thread is 1/40th of an inch. So if we want 3 full threads, that'd be 3/40ths of an inch. If we're going, belt and suspenders here, then 2 times the 3 over 40, and that's about 0.15 inches. And then of course this screw also needs to get through the bracket component. I mean, that's what we're using it for. So we don't want to forget that. And we have to add in that 1/4 inch, and we end up with a screw length of about 0.4 inches. If we go look at a catalog, we're going to see that 0.4 inches isn't a commonly available option, and the nearest fractional size would be 3/8 of an inch, 0.375, pretty close to 0.4 inches, and we already have a lot of factor of safety in there. So we want a 440 3/8 black oxide steel screw. How will we get it? If we go to McMaster.com, we can find one pretty quickly. So here we are at McMaster Car. This is a great supplier for machine elements. There are lots of other ones out there, but this is one of my favorites. And if we type in screw in the dialog, we're going to get this nice search pop up here where we have a bunch of different options we can choose. And we're right now operating in the inch system, so let's click that right away. The first thing we want to choose is whatever is most important to us first. And there are 2 things that really matter the most here, which are the material and the size of the screw. So we said for 40, if we had some exotic material or an exotic size that was really important, we want to choose that first. So let's click on 440. That's going to set the size, and then we're going to skip a bunch of other stuff that we don't care about as much yet, and pick the material. I'll say steel, and we're going to pick a black oxide finish. This is case hardened, very nice hard and high yield strength material for our screws. All right, great. So those are the first 2 things we cared about the most. And the next thing we care about is the length. And we said 3/8. So let's scroll down a little bit and click 3/8. And now over here, we'll see that we've got a bunch of different options. And you can pick from the remaining options as is convenient for your application. But let's say we want a socket head. It's a very common basic machine screw type hex drive. So you can use an Allen key. We want a standard profile instead of a low profile. It's a little bigger, but it's stronger, and the drive strength is higher. And then, okay, our head diameter and threading are set. Head height, I think these are pretty close to each other. So basically, we've got things decided. And then, I guess there's a couple other options over here that aren't in our standard dialog. This would be your typical alloy steel socket cap screw, and you could buy, let's say, 100 of these for $9. Not bad. And we've got some exotic variations down here. This one has a flange. This one has a patch of thread locker on it, so that when you attach it, it'll keep it from working itself out. This one has a hole through it, so you could put a wire and so on. And we would probably pick this first basic version. All right, great. So that is how we walk all the way through the process from a sketch of an assembly to a part number for a screw that we like to pick. And that is a lot to take in. So this would be a good time to take a break, step away, walk around the block, stare out the window and stir your coffee, and then come back in a few minutes to do another exercise. All right, rested up. So our next exercise is the selection of a shaft and bearings. This is another really common problem that we'll run into when designing a mechanical system. It comes up a lot. So it's a good case, and as with the screws, it shares similarities in the overall approach that we'll use to do it with the selection of any catalog component. So here's the situation that we're going to use in our example. We have this gear that is being driven by, say, a motor or some other element that's applying a torque to the shaft. So we've got our gear here. It's meshing with some other gear. That meshing results in a tooth force on our gear. That's how this gear knows the other gear is there. And if we look at this from the side, and we've done sort of a section view so we can see everything that's going on, we've got that tooth force is going, say, into the page on the gear. The gear is rigidly mounted to our shaft here with this hub. Maybe it's a split hub clamp. That's my favorite way of connecting the shafts. It's very precise and results in a high transmission torque. And then the shaft is supported by bearings. So we have some kind of bearing over here and some kind of bearing over here. And then I guess there's some washers in here that keep everything aligned axially and keep that gear from wandering from side to side, which would be undesirable. Okay, and our first task here is to select a shaft. And here are some values that we can use later in the exercise. 100 pounds force at the tooth and pitch diameter of 2 inches for the gear. So first, to select a shaft, let's think about our overall strategy. And once again, here we're trying to think, what properties do we care about? And what steps will I go through to figure out what values I want for those properties? All right, so take a moment, think that through, really map out your process step by step, and then come back. And you can hit pause now. All right, that go a little smoother this time? So with a shaft, again, the thing that we're really going to be worried about is strength. And the properties of the shaft that will affect strength are, again, the material, that'll be important, and the size, and particularly, again, the diameter. That'll be the thing that most affects strength. We'll also care, of course, about the length, which will have to do with the size of the other components to make sure that everything fits together as expected. And that should be enough to get us pretty close to a part number. So, and the process, hopefully, that we thought about was that we need to figure out what's the load on the shaft, or the loads, and then do an inverse analysis to solve for the key geometric parameter, in this case, the diameter. So at this point, you have enough information to actually go through this whole process. So why don't you hit pause in a moment and do your free body diagrams, do your inverse analysis, and solve for the parameters here and make some guesses about the other choices we have to make. All right, so hit pause now. And oh, this should take about 15 minutes or so. All right, big dive there. Did you work your way all the way through to a part number? So awesome. If you stumbled along the way, that's okay. We're going to walk through an example. So the first thing to do is to perform a free body diagram analysis again. And then we're going to see this happens over and over again in mechanical systems design. And that's why we really emphasize free body diagrams right out of the gate and stress analysis, because these are very common foundational approaches that come up frequently. So here we have a free body diagram of our gear plus shaft. Now we could do a free body diagram just of the shaft and that would work out. But in order to know what the gear does to the shaft, we would need to also do a free body diagram of the gear separately. And this is just a little bit faster. And so here we've got the tooth force represented, and we've got this torque that we applied represented. And then there's also going to be some force from the bearings. If there wasn't a bearing force, that tooth force would cause the whole thing to shoot off. And what we'll see is that if we perform a moment balance about the center of this shaft, and we perform that moment balance in the z direction, so along the axis of the shaft, we're going to get that this tooth force causes a moment so it has a radius, and that radius is 1/2 the pitch diameter. And then we have the force of the tooth, so that, lever arm times the force gives us a moment. And so that will be 1/2 of the pitch diameter times the tooth force. And then this applied torque on the shaft also gives us a moment, and that's just T, we've called it. And then the bearing forces don't produce any moment about that center of the shaft because they go past through it, so they have 0 lever arm. And so we can do this to see that the torque that the shaft experiences is 100 inch-pounds. Now, torque, we know, will this torsion loading will result in a shear stress, and that the maximum value of the shear stress, just like with bending, we had sigma is my/I. For torsion, we have tau is Tr/J, or equivalently T times D/2, which is, the radius is 1/2 the diameter times J. So this is our key equation to design this thing around torsion. And we want that to be equal to the maximum allowable shear stress divided by the factor of safety. For a circular cross-section, we know that the moment of inertia is pi d to the 4th divided by 32. If we plug this in and chug through and we solve for the diameter, we're going to find that the diameter is the cube root of 16 times the torque times factor of safety divided by pi times the allowable shear stress. And this is also in the topic reading, so we did some of this math for you already, and maybe you just went to that equation straight away. So this is going to give us a way to solve for the diameter that exactly hits our desired factor of safety, given a material and given that we already know what torque it needs to take. Now, you might also have thought about bending in this shaft, and that is another way that we could figure out a peak stress, and there will be some bending. This is a 3-point bending problem with the bearing forces being offset from the tooth force, and that will lead to bending stress, and that could set the diameter as well. And we provide a solution to that problem in the topic reading. It will turn out, in this case, if we make some reasonable guesses as to how widely those bearings are spaced, just based on our drawing, that the bending stress will be less of a concern than the torsional stress in this case. But we could have worked through both of them and compared if we made some guesses about the displacement there. All right, so working forward with the torsional stress, the diameter that's defined by the torsion loading condition, we have that the torque is 100 inch-pounds, factor of safety is 2, and once again we'll make a guess about the material. Here again, just like with the machine screws, with shafts it's a very good idea to guess at a really hard steel to start out with, because they tend to have very high strength, which results in a smaller, more compact component, and they tend to have very good strength to density ratio, which also, even though it's very dense, results in a lower mass component overall. The yield strength for 440C hardened stainless steel is like 275 KSI, and for steels, usually the shear strength is about half of that value if you don't find a value when you look for a particular material, and that would be 138,000 PSI. If we plug all these things into our equation, we get a diameter of 0.195 inches, and that's pretty close to 3/16 of an inch. Here again, it's close, but it's like 3% bigger than this fractional value, but they don't sell shafting in this diameter, and this is pretty darn close. We've already got a factor of safety 2 in there, so it's probably going to be all right. And once again, we can go to McMaster and find a part. So let's say shaft, and here we're going to want to start with the property that we most care about. We'll stick with the inch system, and it'll be okay to select either the diameter or the material first. Actually, we're getting a lot of diameters, so I'm going to select the material first. And let's go to stainless steel, and then we get to choose an exact type. The treatment matters a lot when understanding material properties. So one stainless steel can be very, very different from another. 440C stainless steel is a just very high-end material, and we'll see it's actually quite expensive. And then we want to go to 3/16 of an inch. I'm not sure what length we want. There's, we didn't give enough information in the problem, but it looked kind of like, given this diameter was 2 inches, maybe we want a short length of shaft. Let's say 6 inches, just as a guess. And then if we come over here and we sort of scroll through, we're going to have a bunch of other options there about surface treatment and so on. But let's just scroll through and see what we get. So okay, here's some shafting that's tight tolerance, bearing quality, 440C stainless steel, $9 for a 6-inch length. Well, that's expensive. We got 100 screws for $9 a moment ago. So this is pretty expensive. But it can get even worse if we come back up to this. I saw this was a linear motion shaft. Let's see. We've got, this thing is going to be $50. Oof. So if we use these high-end materials, and especially this will be a precision ground polished surface finish, very, very fine, and that means it will have very low friction, and it will be very precise for interaction with, say, the ball of an open ball bearing in one of these linear cages. And it will probably wear really well. So all of those things are great, but they come at a big price. All right, so we were able to work through the whole process and select a shaft. Now let's do the same thing for a bearing. So first, I'm going to do strategy again. So think about, what are the properties of the bearing you're going to want to pick? And what is your process going to be to select them? And you want to have a step-by-step plan in mind before you proceed. So hit pause now and work that out. It should take a couple minutes. All right, you have a plan? Great. Hopefully you saw there are a few choices that you're going to want to make here. So one is, what type of bearing do you want? Like, do you want a ball bearing or a bushing, for example, or a needle roller bearing or something like that? Another is, you're going to want to know what is the inner diameter of the bearing. That's going to be important. What radial load should the bearing be able to take? And then what part number do we want from McMaster to get that bearing? And then the processes we'll want to use here are, for type, we're going to think about what is the application and what are the strengths and weaknesses qualitatively of different kinds of bearings. And we might do the whole process for multiple bearings and then compare our answers. For diameter, that we're going to think about, how does this bearing interact with other elements in the system? We want to make sure they're compatible. And for radial load, we'll again use a free body diagram to understand how the bearing is loaded and make sure that it can sustain that load. All right, so now work through that whole process. It should take a little while. It should take maybe 15 minutes. And then when you have your part number, come back and we'll walk through one example answer. Oof, you get it? All right, so here is one example answer for this problem. So we start always with a free body diagram. And once again, we're going to do a free body diagram of the shaft plus gear. And here we're looking at it from the top view because it makes it a little clearer. And we'll see we've got this tooth force in one direction, and we're going to want these bearing forces in the other direction. And if we do some of the moments about this point, we know that needs to be 0. And from our drawing, it looked like the distance to this bearing and that bearing was about equal. And so we'll have some length there, and L times F bearing 1 is going to be minus L times F bearing 2 should equal 0. And so the two moments will be the same, and then the length will fall out. And that means that the bearing on the top, the force on the bearing on the top has to be equal to the force on the bearing on the bottom. So hopefully these kinds of moment balances are happening quickly, just in the back of your mind at this point. You can see that these two forces should be equal. And then we have the magnitude. So we know that we've got the tooth force going that way, and we've got these 2 bearing forces going the other way. So each of those bearing forces should be 1/2 the torque force if they're equal. So the radial load on the bearing will be that we want to specify will be the factor of safety times the bearing force. Well, okay, we're back to the tooth force, and that's going to be 100 pounds. And we're going to want to find a bearing that has the same inner diameter as the outer diameter of the shaft, because we want them to fit together. So want to check to make sure that that works out. And then we'll want to make sure that the bearing has at least the rated load. So here we have the bearing force is 50 pounds, factor of safety is 2. The inner diameter that's required is that we'd like to have is 3/16 of an inch. If that didn't work out, we would go back and iterate and select a new shaft. Maybe if the bearing diameter is too big, we would pick a lower density, lower strength shaft material, so we'd get a bigger shaft that was still close to optimal. And then we are picking a ball bearing type for this case. Again, you can do it with a sleeve or ball bearing. Many times these work out to be really similar, but the reason we guess at a ball bearing here is because it has a very, very low coefficient of friction and can be very precise, which is helpful for making custom gear sets. All right, so we're going to return to McMaster Car to try to find our part, and we'll type in bearings, and then we'll get a bunch of options of different types of bearings, and we'll select ball bearings. That's the type we'd like for this application. And then we have on the left these choices of characteristics. The first thing we're going to choose in this case is the inner diameter that's going to set the shaft diameter. We want that to be consistent. So we'll pick 3/16 of an inch. And then there are a bunch of other characteristics we could choose over here, but you'll notice if you look carefully that the radial load is not listed, and that's because we've already got a fairly narrow range just by selecting that shaft diameter. And so here we'll see that for each item in our list, we're getting this radial load capacity in pounds. And here the static load is refers to the case where the bearing isn't rotating, where it just sits in one configuration for a long time, and ball bearings can accept less load under those conditions. Dynamic is if it's continually rotating. That results in a little bit more favorable loading of the balls inside the ball bearing. So let's see, 290 pounds. We were looking for 100 pounds. Let's see, all of these are greater than or equal to, oh, well, this is a little closer, but a little under our target. So we have a bunch of different options that we can choose from at this point. And then we look at things like, does it have the flanges that we want, the seal that we want, the kind of lubrication that we want, those sorts of less important things, what's the outer diameter, what's the width, and pick things that are convenient for our system. Okay, so now we've gotten all the way through to selecting an actual bearing. So if we look back over these 3 exercises, what we can see emerges as a really consistent strategy here is that we're gonna guess at the kind of type of component and maybe material. We're gonna use free body diagrams to get the loading. We're gonna use inverse analysis to figure out the key parameter values, like the diameter of a machine screw or a shaft. And then we're going to check to make sure everything that fits together as intended. And if it doesn't, we'll iterate. We'll go back and adjust some assumptions and re-optimize those parts. And hopefully what you notice is that this process is exactly the same as the one we've used for our custom components. It's kind of like we're designing these catalog parts as custom parts. It's just that there's a really good starter design out there already, where we're just tweaking, say, one parameter to meet our needs. All right, so you're now ready to go out and incorporate these kinds of elements into machines that you design. Happy designing.